Let's take a look at rational inequalities, the second topic of section 8.5. We want to look at our procedure for solving these inequalities. We want to make sure we're expressing the inequality in standard form, where we have 0 on the right side of the inequality. So we'll either have f of x less than 0, or f of x less than or equal to 0, or f of x greater than 0, or f of x greater than or equal to 0, where f is a rational function. And notice f needs to be a single rational expression. So that's another key point. We're going to solve the equations that result when we set both the numerator equal to 0 and the denominator equal to 0. The real solutions to these equations are called boundary points. Locate these boundary points on a number line, and just as we did with the polynomial inequality, we're going to divide the number line into intervals. We're going to choose a test number, a representative number within each interval, and we're going to evaluate f at that number. And if the value of the function is positive at that test number or representative number, then the function is positive for all the numbers in that interval. If the value of the function is negative at the test number, then the function is negative or less than 0 for all numbers x in that interval. We're then going to be able to write the solution set, selecting the interval or intervals that satisfy the given inequality. So let's look at this procedure for x minus 2 over x minus 6 greater than or equal to 0. Notice that we get to skip step 1 because the polynomial is already in the standard form, where 0 is on one side of the inequality and a single rational expression is on the left side of the inequality. Now in step 2, we're going to solve the equations that result when I set the numerator equal to 0. That means x is 2, and the denominator equal to 0. In this case, that means x will be 6. Remember, these are my boundary points. So now I'm going to take the number line and I am going to place the boundary points on that number line. 2, and 6. Now notice that 6 makes the denominator 0. So 6 could never be a solution, part of the solution set. Since the inequality has the equals to in it, the number that makes the numerator 0, as long as that number doesn't also make the denominator 0, is in the solution set, because the expression will be 0 when x is 2, because I'll get 0 over negative 4, which equals 0 when x is 2. So I'm going to make this a solid circle to remind myself that 2 is in the solution set, but I'm going to leave the circle above 6 unfilled in or open because 6 is not in the solution set. 6 makes the rational expression undefined. 2 makes it 0, and this inequality says, give me the x values that make this expression 0 or bigger than 0. All right, so the interval that is not, now I'm getting ready to do my fourth step. The interval that's represented by this portion of the number line, remember now I'm looking for the numbers that aren't boundary points, are the numbers less than 2. And this is the interval that represents those numbers, negative infinity to 2. The next set of numbers that are not boundary points are the numbers between 2 and 6. So the interval 2, 6. And notice these intervals, the test intervals, never include the boundary points. Even if one of the boundary points is going to be part of the solution set, the test intervals do not include the boundary points ever. The solution set may. And then the third test interval are all the numbers bigger than 6. So 6, infinity. All right, and now let's set up test numbers, or representative numbers that lie in each of these test intervals. Here I'm going to choose in the interval for all numbers smaller than 2, I'm going to choose x equals 0. If 0 is not a boundary point, then I always want to choose 0 when I get to the test interval that contains 0, because 0 is very easy to work with. In this second test interval, I'm going to choose x equal to 3. You could choose any value in the interval, but you do want to make your choice a simple number that makes your work easy. In the third interval, all the numbers bigger than 6, I'm going to choose x equal to 7. And those are my test numbers. And let's remember our inequality. Okay, so remember, this is our inequality, x minus 2 over x minus 6 greater than or equal to 0. So we have our test numbers, and we are going to replace x with those test numbers in the inequality. So 0 minus 2 is negative 2. 0 minus 6 is negative 6. And the inequality becomes negative 2 over negative 6 greater than or equal to 0. So this negative 2 divided by negative 6 is actually positive 1/3. So this becomes, the inequality when x is 0 becomes 1/3 greater than or equal to 0, which is true. So that essentially means all the numbers in this interval, all the numbers smaller than 2, make the inequality true. Now let's let x equal 3. 3 minus 2 is 1. 3 minus 6 is negative 3. So the inequality when x is 3 becomes negative 1/3 greater than or equal to 0, which is false. And we could write that like this, of course. We can have the negative in the denominator and the numerator, or level with the fraction bar. And so, since the test number makes the inequality false, all the numbers in the test interval will also make the inequality false. Now let's let x equal 7. 7 minus 2 is 5. 7 minus 6 is 1. So we get 5 over 1 greater than or equal to 0, which is simply 5 greater than or equal to 0, which is a true statement. Since our test number makes the inequality true, all the numbers in the test interval that test number came from also make the inequality true. So we see that for the interval of numbers smaller than 2, the inequality is made true. And for the interval containing the numbers bigger than 6, the inequality is made true. And then we remember that the boundary number or boundary point 2 is part of the solution set, but the boundary point 6 is not, because it makes the rational expression undefined. So the solution set of this inequality are all of the numbers less than 2, including 2. So to show the 2 is included, I put a bracket around the 2. Unite it with all of the numbers bigger than 6, which is the interval 6 infinity. All the numbers smaller than 2 is the interval negative infinity, comma 2, including the 2. And that's my solution set.